We are very honored today to welcome Dr. Mohammed Samadi in this seminar. Dr. Mohammed is the head of the research and development at Wasila, working with artificial intelligence and machine learning in indoor navigation. Before joining Wasila, Dr. Samadi held a principal research role at BlackBerry Canada, working in advanced connectivity issue, including video over wireless traffic modeling, wireless coexistence, and quality of experience metrics. In 2004, he co-founded Ergo Wi-Fi, which designed and built low-power, solar-powered outdoor Wi-Fi networks. Dr. Samadi is the inventor of more than 30 granted and pending patents, the author of several invited book chapters and referred conferences and journal papers. He holds a PhD and MSc and Bachelor of Engineering from McMaster University, and currently hold an adjunct position at the Engineering and Electrical Department. So the talk of today is indoor navigation, a use case of particle filter, which is in-field experience.
Thanks for the very warm introduction, and I hope I will not fail to share some of the knowledge and benefit with you. The topic today will be about indoor navigation as an application of particle filters. I chose the topic, one is because this is what we're working on as an industrial company, and two is because particle filters is really, it's an interesting and a recent adaptation of a more well-established class of techniques called genetic algorithms. I will be talking about the problem scope, some of the techniques applied to address this problem, and then specifics about the particle filter and how we adapt it for indoor navigation, and then some of the in-field challenges that usually are not necessarily mentioned in academic papers. This is stuff that we see in the field when we go to actually implement such systems, and perhaps how can those be modified or adapted to become problems worthy of the academic community. So mega venues are popping everywhere: malls, airport, hospitals, themes. Say about a decade ago, there was a competition, perhaps more regionally than anywhere else, is to build bigger, and bigger was always better. And then people who built malls and airports realized this was architecturally a problem. People were having such a hard time finding their location or their desired destination within certain facilities. And from an architectural perspective, there is a shift in paradigm recently that bigger is not always better. And people with the advent and wide adoption of applications such as Google Maps, they want that experience to carry indoors. So if you come to the university here and you get lost, some people, probably their immediate reaction is to actually open their Google Maps and try and use it before they realize that GPS doesn't actually work indoors. And providing such experience indoors has proven to be very challenging because GPS does not penetrate walls, and the environment is continuously evolving. So if you go to a mall, there is a shop here today. In probably a couple of years now, the shop has been demolished and erected somewhere else within the mall. And the likes of Apple and Google are inching away at solving this problem. This problem has been the focus of both the academic and the industrial community for a while, but until today, there is no one solution that fits all. There is no one solution that fits every venue. And there is no standard today. There are some standards who are being worked on, but there is no standard today available in the industry that we can go and buy that will solve this problem for us. So in the next few slides, I will discuss at a very high level some of the techniques which are applied to solve the indoor navigation problem. The very basic and the most primitive of them all is RSSI-based triangulation. So we use the reverse of a propagation model. I know the RSSI, and based on the RSSI, I will do an estimate of the distance, and I will do the estimate of the distance with respect to multiple receivers, and then I use basic triangulation techniques by drawing circles, and I will establish the location of the user based on these techniques. The problems, as we can see from that figure, is the error in propagation techniques or the reverse of propagation techniques is high. Propagation techniques are really meant to capture the quote-unquote the average, log normal path loss, line of sight path loss, etc. They're not really meant to give you an instantaneous. And if they are meant to give you an instantaneous, it's usually part of a simulation platform that requires Monte Carlo simulations, okay? So usually the error is fairly large with such a technique. It's basic, it's primitive. It probably can narrow down the area of the user to a certain section of a building, but can't really pinpoint the location of the user. Someone thought of a slightly more sophisticated technique called time of arrival. So basically, the system is based on the exact measurement of the arrival time of a signal transmitted from a mobile device to a receiver. Because the RF signal travels with a known velocity, and we have the time, then we can estimate the distance between the TX and the RX pairs fairly accurately. The problem, this works really well, but the problem is it requires knowledge of the TX time, the transmission time, and the reception time correctly. And the TX time isn't necessarily available. When we have a smartphone communicating with a Wi-Fi access point, a Wi-Fi router, the times are not necessarily synchronized. The times between the clock and the access point are not necessarily synchronized. So someone smart came and thought about a refinement of the system, the time of arrival system. They said, we cannot necessarily synchronize the smartphone to the Wi-Fi router, but perhaps we can uniform or synchronize the time between the Wi-Fi routers themselves. And then they came up with a technique called time difference of arrival, which is basically if I have three receivers or three transmitters, depending on who's doing the calculation, and a target. And this target is transmitting. Now, the signal is received here, and the signal is received here. We use the time difference in the reception between this and this, between the two receivers, okay? The time difference in the reception at two different receivers, right? And then we call that's delta T, and then we know the C, and then we figure out delta D, which is basically the differences between the distance between the target and each one of these, which is really an equation. Delta D, which is this, is actually the x coordinate or the location, the Cartesian coordinate difference between the beacon and the target, and then the beacon and the target, and that would be delta D. This is nothing but an equation. This is in 2D. This is nothing but an equation of a hyperbola. So we then apply nonlinear regression techniques with a lot of pairs, right? And then the intersection of these hyperbolas is actually the target location. I repeat. So this is basically, I know delta T. When the signal is received at beacon 2 and beacon 1, I know the time difference between these two receptions. I know that propagation speed is C. The multiplication is delta D. But delta D is nothing but the difference between the location of this beacon to this target in both x and y coordinates and the location of this beacon to this target. It's a hyperbola, right? And then if you have a large number of these hyperbolas, and you take all these combinations of the beacons, so in this line, for example, it's beacon 1 and beacon 2, this is the hyperbola. And then this is beacon 2 and beacon 3, this is the hyperbola. And then this is beacon 3 and this is beacon 1, this is the hyperbola. And then you look at the intersection, you solve the equations for these hyperbolas using nonlinear regression techniques. The intersection is the location of the target.
But C is not necessarily constant, because you might have different media where it's traveling through.
Sure, it will be the media that you're traveling in, right?
Yeah, but you might have different medias, you know, and C will not be constant.
Let's say that we are a line of sight in this room. C will be the same everywhere.
Yeah. Just in this room. But if you are in a place where you have different, you have concrete, you have wood, you have other things, you will have a problem.
You will reduce the accuracy. You will reduce the accuracy. You won't have a problem to the point where you will reduce the accuracy. This, if you are perfect and the synchronization was perfect, then that with 3 hyperbolas, you will get the exact location. Any variation in delta t due to synchronization or c due to different media, then that will add to your accuracy, inaccuracy to be specific. Now, again, continuing.
I'm sorry, but if you have more than 2.
You have 3. You need 3.
Yeah,
You need 3.
No, but I mean the intersection point. If it's in 3D, then you have 3. But you could have more than 1 intersection point.
I didn't want to complicate, yes, but then then you would need multiple iterations over time to rule out. The equation here will actually always result in 2 hyperbolas, right? So there's one that is unreal, and then there's one that is real. The one that is real is carried forward by multiple iterations, right, over the same pairs. This requires cross-receiver synchronization, which is again a strong requirement on receiver clocks. So something like this is doable, for example, on a GPS-like system, but on a cheap chipset like Wi-Fi, for example, this is somewhat difficult to achieve, right? And that's why we don't see these techniques necessarily used today still.
I'm just thinking aloud. If you have different manufacturer of Wi-Fis,
yes,
also could affect this.
that's could affect this.
This is a good, another
From a chipset perspective, yes. And that's that. To address this problem, there is a new standard that is being discussed. It's called 822.11az that talks about this exact problem. They plan on actually Wi-Fi. There are competing camps in the localization world. There is the Bluetooth camp, and there is the Wi-Fi camp, and then there is the ultra-wideband camp, right? And there is the cellular camp, right? And every chipset manufacturer wants to see their standard to have the widest adoption, right? And then the Wi-Fi response to the Bluetooth camp, Bluetooth is issued beacons, is to actually do 822.11az, which uses time difference of arrival. The next technique is angle of arrival, which is once an angle direction of arrival is established, if we assume there is an oracle, a platform that allows us somehow to establish the location of arrival or direction of arrival, like the figure here, for example, let's say that this is the laptop or the mobile station that we're trying to locate, and here is base station 1 and base station 2, and then there is the angle of arrival, and somehow we manage, and we'll talk about how a sample technique of how to establish that. We establish the angle of arrival. We can extend 2 rays, and the intersection of the 2 rays will actually give us the location of the mobile station. Now, the problem really, this is all fine and dandy in theory. The problem really is to establish accurately and timely the angle of arrival in a heavy multipath environment, like indoors, right? This usually requires a very, is it possible? The answer is definitely it is possible, okay? Has it been done? It has been done. Are there systems out there to do it? The answer is yes. At what cost? At what expense? The complexity of the receiver design, right? And the most common one is music, the algorithm that is used to discern the location of the angle of arrival from a particular mobile station. And where does the complexity come from? Is in the multiple antennas, right, that you actually have to put, right, in the receiver. And then this drives the cost of the system way up, right? For example, Cisco, which is the most common platform for Wi-Fi access points, they have what they call a hyperlocation access point, a typical Wi-Fi Cisco access point. You buy a ring that you attach it to the Cisco access point. It's got a 32-element array, right? But even then, the Cisco indoor location platform requires you to input the location of the access point within 1 inch in 3D. So they want to know the location of the access point in XYZ coordinates within 1 inch in order for them to be able to accurately resolve the angle of the arrival and be able to use that. This is really impractical. Usually those who actually go and install Wi-Fi access point, wherever the closest power plug or the civil wire is running, they put the access point and that's that. This is, and then the last strategy, and it's quite interesting, and this is what we use, or primarily what we use other techniques as well, is fingerprinting. And the philosophy goes that at any given location in indoors, there is a unique RF fingerprint from the different transmitters, right? So if we actively walk and collect data while we're walking, so I go at a location X1, Y1, and I stand here and I say, give me a snapshot of the system, right? Perform a scan, perform an RF scan. Scan all the Wi-Fi access points, scan all the Bluetooth transmitters, and like Dr. Sagaf was saying, even do an augmented reality scan. Scan the imagery, right? And store them as quote-unquote descriptors of this X1, Y1. Change your location and perform another scan. And that will be the descriptor for the X2, Y2. This is repeated for the entire indoor space. Okay? So now we have this something called a fingerprint, a data of a fingerprint. Very much like the police station fingerprint, right? You collect a very large database of fingerprints. Okay?
You said change your location. How do you change your location? I mean, to what accuracy? I mean,
it's the same. If we want to apply, at a very high level, if you want to apply the Nyquist concept, right? So if you have to sample at twice your desired accuracy. Let's say that your accuracy is, you want your system to be accurate to within 3 meters. So you have to get a sample every 1.5 meters. Okay? And then you create this database. Okay? And that's called the offline stage. So now someone went there and they collected the fingerprint and they stored it in an offline database. You store it and you keep it. Somebody else comes at a later time. We don't know their location. They're using their smartphone. They perform a scan. BLE scan, Wi-Fi scan. And then they return the results to a search algorithm, a particle filter, right? That goes and determines based on the similarity of this section of the fingerprint, where the location of the user actually is. Now, if we were in a perfect stationary channel that does not change over time, then there will be, and you're using the exact same device that was used to collect and create this database during the online phase, there will be one row here that is a perfect match, and that's your exact location. But in real life, there is no such thing as a stationary channel, and the device that was collected to create this platform has different characteristics than the device that is being used by the user. Okay? That's one challenge. 2, I collected this, and this took me, say, 2 weeks to collect. So I want to come to this building, and it actually takes me 2 weeks to collect. 6 months later, somebody decides to put change something.
Prepare the router.
Yeah. Right? Take the router down, put a new router, more commonly, probably put a wall or put some platforms that change the RF propagation. This is not, it's a living being, right? 2, so we talked about the differences between this, the antennas, for example. The iOS is very different than Nexus phone or Samsung phone. They're 2 different platforms, right? And then this itself changes, right? So how can we do that? How can we solve this problem? Particle filters are pretty darn good at actually solving this problem. They tell you, I don't have to have an exact match. It's good enough for me to have a group of similar ones. Very much similar like a police station. When fingerprint is unique. But as we age, our fingerprint actually changes. But a good fingerprint matching technique should be able to resolve this over time. And this will be the focus of the next few slides. But before we go there, so what kind of technologies apply these techniques that we described today? We've got Bluetooth Low Energy, iBeacon. Apple has made a big splash about iBeacons. They're basically operating in 2 megahertz. They're periodic beacons, battery operated. They're available in the mobile phone, which makes them really interesting. One can use them for fingerprinting, and their primary use is really proximity-based marketing. If you get close to them, a message shows up on your phone, you know, such and such store has made a sale. Wi-Fi, classically speaking, probably every Wi-Fi access point here is operating in the 20, perhaps the 40 megahertz, it's 802.11n. Recent ones with 11AC, they're operating at 80 and 160, which makes them really suitable for ultra-wideband applications. A very interesting problem is the greatest majority of Wi-Fi deployments are deployed for data usage. When we deploy Wi-Fi today, why do we deploy it? We want to use data. That's a different requirement than applying it to perform indoor navigation. So we may have a perfect network for data usage, but it will not necessarily give us good accuracy in terms of indoor positioning. The channel state information is not available to us through chipset providers. And from an industrial perspective, this is somewhat crazy when you think about it, like a company like Qualcomm. Qualcomm wants to know your location. Believe it or not, for whatever reason, Qualcomm, the company that provides chipsets, they're not even providing phones. They're interested in your location. And they may be able to get at that location, but they may not necessarily give it to Google or Apple. So even chipset manufacturers are starting to inch into other like the whole ecosystem is just becoming spaghetti. Ultra-wideband, it's basically a new technology. It's up to 5 megahertz, which basically allows you to resolve the first arriving ray with very high degree of accuracy. But the data rates over ultra-wideband are much lower than Wi-Fi, which explains that why it's not adopted yet. VLC, a couple of weeks ago, I got a call from Philips in Netherlands. They said, we're interested in sending you 4 lights to try in your system. So why do I need to try 4 lights? They're modulating these lights according to a specific pattern. So when you open your camera, you can detect that modulation and determine your location. Passive RFID, it's basically choke points. A chipset gets activated based on the signal transmitted from a transmitter and then it reports back its location. The disadvantage of passive RFID is that once you enter a zone, you can't really know the location of yourself within that zone. Virtual reality is basically the use of imagery. The problem with virtual reality, it's really interesting, but the amount of data that you have to capture, images are very rich. Both when you store them offline and during the online phase, we keep capturing the data and transmitting. That channel is extremely active, right? And dead reckoning, which is extremely interesting. I can use sensors, accelerometer, magnetometer, and gyroscope, which are available on the phone to determine someone's location. Accelerometer will be able to tell me the number of steps. So if I can assume that a human's step is about centimeters, and I just do step counting, I can determine the displacement. The magnetometer is really a boussole, it's a compass, right? Can tell me the direction, right? The gyroscope tells me the angular speed. So I can fuse all these, usually using a Kalman filter, to give me my location, right? The problem with this, so displacement, direction, and rate of change will allow me to establish my location, or at least the path that I traveled. The problem with this is these sensors have a lot of drift. So they're very good in giving me my location for, say, a minute to 2 minutes. But after that, the drift is the error is too large in these readings, especially the the magnetometer and the gyroscope. So what people do,
The phone has all these things?
yes,
Yes.
yes. And now, and sometimes multiple of these things. So you could do double integrals and you could do validation or whatever, yeah. So what people are talking about or talked about is, maybe what we need to do is, for example, use Wi-Fi plus this. So once in a while, we recalibrate. You establish your location, and then you have now, from now you have 30 seconds using the sensors. After 30 seconds, you must have another Wi-Fi location or another BLE location, okay? Which is really, really interesting.
Actually, in Kalman filter, we have what we call measurement update.
Yes,
Exactly
yes,
the same thing.
yes, yes. Very, very, yeah. Actually, the most common technique for this is Kalman filter, right?
So, this kind of RF-based strategy, but
This is not RF-based. This one here
the last one, yeah.
Yes.
That reminds me, for example, with the magnetic, they call the magnetic print, I think, or
Yeah,
fingerprint.
it's exactly
the same kind of magnetic-based
No.
magnetic field.
No, magnetic field. So that would be Indoor Atlas, for example. The
Indoor,
system.
yeah,
Yes.
that's
Okay.
from that.
That the name of the company is actually Indoor Atlas. That's used. What they're saying is very similar to RF fingerprint at a given location. There is a very unique
Fingerprints.
electromagnetic. Yes. From the Earth's magnetic core,
Yeah.
right? The problem is, again, we're deploying a system at Ferrari World, and they have these huge roller coasters with big magnets. So you're walking, and all of a sudden the roller coaster passes by you, and then the compass, right? It just rotates, right? Because now there's a huge. There are techniques you can apply the gyroscope. The gyroscope is not affected by the magnet. You can say, my gyroscope is not indicating a rotation. So you can't ignore it. You can't ignore that compass reading, right?
What's the difference? What is the cause of it, or can we reduce it? Can we
The physics. I'm not a physicist, but it's
Actually, this is what is used in UAVs and we use it in
yes.
inertial navigation system.
And in planes, actually, the very first application of dead reckoning is in the 70s, but these were $100,000 systems in planes, basically the autopilots and whatnot. Okay. We don't work on this a whole lot. We are a consumer of this, but I know there are lots of people, especially in nano and physics, really, who are working on the physics of the sensors, right? Interesting area, nevertheless. Particle filter. The next few slides, I will talk about the particle filter. So, a particle filter, there is a state. In our system, it's the location coordinate. And that is hidden. We don't know the state. There is an observation that may tell us about the state. That's an observation. In our case, it's the RSSI values. So there is a relationship of a known function that captures the relationship between x and y, usually the distance, right, and the environment. And there is a relationship that captures x at time 0 with x at time 1, which is basically the mobility model, how the movement, precisely. A particle filter is designed for a hidden Markov model, where the system consists of hidden and observable variables, like we talked about, hidden and observable. The observable variables are related to the hidden variables, observation process, to the state process, by some functional form that is known. Similarly, the dynamical system describing the evolution of the states is also of a known probabilistically, right? If I am at this location, I could either continue walking this way or I could go that way. The filtering problem is to estimate sequentially the values of the hidden state given the values of the observation process at any time step k. A typical Bayesian
So that means it's an online algorithm, is it?
It is an online algorithm, right? All Bayesian estimations usually estimate the location xk given the observations all the way y0, y1, all the way to yk. Whereas a particle filter, not only it uses this, but also combines, when this is the novel piece, it actually combines the location, my estimates of the state itself. Because you are actually, I actually have a simulation output, and you will see, initially you may be wrong, or you may have two estimates of your location, but then you continuously converge, right? As we will see. So this is from an actual venue. This is a sample real fingerprint. Basically, we divide all the walkable paths. We walk them. We send people to walk them. Then we collect data. And data, at each XY coordinate, there is data that is stored. Sometimes we make the line multiple times, this way, that way, to capture all the RF vagaries, right? And we may use multiple devices. So we capture the different antenna patterns, right? And different antenna gains, different antenna patterns, different receiver sensitivities. Here is the math, and here is a simplified explanation. Initially, a particle filter is you're saying, you're making a large number of hypotheses. You have your fingerprint, you have your database, and you say, I want to assume that my location is 1 out of 500. So I spread 500 particles, I choose 500 records from that database. It says, it's got to be one of these 500. That could be right, that could be wrong. Usually you start with a uniform spread. So you make an initial by making a large number of hypotheses, which is basically selecting many rows from the fingerprint at candidate locations. Then we test each one of these hypotheses one at a time. And the way we do it is we perform a scan during the online phase. The visitor to the mall or the visitor to the university performs a scan. Says, here's my scan. And then you compare that scan, the observation piece, the RSSIs, to each one of these 500 assumptions, the hypotheses. How do you do the comparison? You can compare it in Euclidean distance and in terms of the RSSI I'm talking about. Like you compare the RSI to the RSSI. Or there are many other techniques. So each one of these hypotheses gets, quote unquote, a weight based on the similarity between it and what the online user is actually seeing. Clear? Or
yeah.
Okay? And then, so now I have these 500 hypotheses. Each one of them has a weight. Likelihood. Is it very likely or not very likely? Okay? Locations with the highest similarity or the highest weight are kept. I keep them. And those with the least, I don't throw them away, but I take their weight and assign it to those with higher weights. Improve based on the likelihood. The surviving hypotheses are used to generate the next round. So basically, let's say that I actually have made, out of this 500, I found, took the 100 that have the highest weights. Then I could say, okay, fine, these 100. Are they really concentrated in one area? If they're concentrated in one area, I will calculate the arithmetic mean, and I will assume, to begin with, this is my starting location. If they're not, then sometimes I may decide to perform, if they're very spread, I perform clustering. Are they spread in 2 locations? Then here, I have 2 locations which are possible. Next, I use these 100 to say, here are 100 possible locations. They have very high weights. At time t plus 1, if each one of these hypotheses was to take 1 step, where would they be? Or 2 steps, where would they be? And I would actually go into my RF fingerprint and identify these. And this will become my search space for the next iteration.
Is there a smart way of choosing the first initial hypothesis?
Yes. You do what they call a first stage filter. I'll give you an example. Let's say that in a park like this or an indoor venue like this, there is simply an access point that is here, and you are seeing this access point. There is no reason for you to go and choose particles which are here, right? So you only choose particles which are in this area. Weight assignment is in itself is just a complete branch. Like how do you actually assess? How do you assess the similarity between the hypotheses and your hypotheses, which are selected records from the database, and what the user is seeing, right? Sometimes it really should capture the noise in your physical phenomena. So if we're talking about RF, it's when you're standing at a given location, from time t to time t plus 1, your signal may change according to, say, log normal path loss. So the weight capture that. The weight assignment formula captures this, right? The closer the particles readings to an observation, the higher the particle's weight. Resampling is really, at one point in time, particle filters started to fade away because there was a key problem. And then some guy came and realized, we can solve this problem, which is your hypotheses with very low weight, the people used to use them, but they're very low weight, so what do I do with them? So someone said, we need to resample. Resample is basically used in particle filters to overcome particles indegeneracy problem, which is when particle weights drop to very low values due to the fact that the weights are calculated sequentially, right? So resampling duplicates the particles with higher weights and removes the particle with lower weights. So it's basically you're saying, particle with lower weights, I'm going to throw you away and give your location to somebody else who's got a higher weight. And I will cap it here in terms of resampling. Propagation and prediction. This is really the system state at each step t is calculated based on the previous time step. In our system, let's say that I found a location based on the RF fingerprint. Then I come and use the sensors which are available on the phone to tell me how many steps I walked over a period of, say, 5 seconds. And this is what I use to propagate my particles inside my fingerprint. So if we go back to this particular one here, let's say that I chose this particle. And this particle was one of the hypotheses and actually had a very high weight at time t. At time t plus 1, I take this exact particle and I propagate it. Where do I propagate it? Which other particle do I replace it with? I go and say, okay, this is x1 and y1. This is the most likely location for the user. If I use the sensors, is going to be this. So throw this one away and replace it with this one. That's called propagation, and it's dependent on the mobility model. After a while, as we will see, the particle filter converges when the output of the prediction phase becomes very close to the output of the particle filter. Basically, after a while, more and more weights will be assigned to those observations which are closer to what the end user is actually seeing. And then your arithmetic mean will start to converge to the location of the user. I have a video here, taken actually from live measurements. Let me see if this is okay. How do I play this one here? Okay, so the red ones are the particles that we started with. Basically, like you said, there are lots of particles. We chose a subset of particles initially. These are our 500 hypotheses. Okay, went very quick. Okay, the green. The green is actually the actual location. The blue dots are the particles, but with their weights assignments. There are small blue dots and there are bigger blue dots. Yes. The bigger blue dots are those which are closer. Obviously. Right? And then I only consider a threshold. I say anything below this threshold, ignore, and only consider the arithmetic mean of the blue dots which are bigger. And then give me the average, the arithmetic mean, and that's the red dot. So the green dot is the actual location, and the red dot is the estimated location. It's pretty darn accurate. And then let me Okay, let me just go back here. Okay, now the black is I took every blue dot and I propagated it where it is possibly going to go, right? Sometimes, for example, here. See, but this is not a possible location. How is it possible that there is a particle here? In your particle filter, you want to make sure that the spread continues to have a high standard deviation, because in the likelihood that your first estimate was wrong, you want someone else, another hypothesis that's far away, to actually bring you back to reality. So, and this is
it a kind of exploration, like an exploitation of the space, is it?
it does exploit the space, yes. Yes,
yeah.
yes, yes. So as you can see, the green dot is the actual location and the red dot is the estimated location.
It's keep nearer and nearer to it.
Yes, yes, right. And what's interesting is you can see that the particles are moving, like, because every time you move, you're propagating with, right? Okay. Let me, and that basically that concludes my talk. I just would like to some of the problems we're seeing actually in the field, right? And some of those are actually pretty novel in a sense that you can't find really academic papers to address them. They're really stuff that we see in the field, which is basically the collection. Sometimes during the collection phase, if you collect using a smartphone, the smartphone may not necessarily collect all the data that all the RF signals that you're seeing, right? So your observation subset becomes really weak. You miss sometimes some of the RF transmitters. The fingerprint size. You have a huge fingerprint size. Do I really need all of it? If I perform the principal component analysis on it, from one row to another, what value do I have? Because when you have thousands and thousands of rows of data, searching becomes expensive, right? Fingerprint density and sparsity and uniformity. If for some reason one area of the floor was represented heavily, people walked on it multiple times, right? At the end of the day, when you choose your 500 particles initially, or when you choose your particles, especially if you chose them uniformly, that area with a very large density of fingerprint will be overrepresented in your hypotheses. And the probability of a location estimation in that area will be very high. So how do you deal with it? How do you deal with this? Like sometimes if you have a wide path and a narrow path, the wide path gets overrepresented in the location. That's wrong. Maintenance over time. How aging techniques. How can I update without actually doing a site fingerprint? This is really interesting, basically using some crowdsourcing techniques. Scalability. It's one thing to implement a particle filter in MATLAB, and then when you actually go to a real life implementation, when you have 5,000 users using it, and you want the system not to collapse. So talk about, for example, GPU-based implementations.
In terms of time, how long it will take for time frame to identify or localize it itself for the particle filter?
Well, it depends on the kind of CPU that you're using.
Roughly,
So if you go back from a queuing theory point of view, you cannot have two subsequent observations, two scans, without having a location. Otherwise, your queue will grow unbound. So in our system, for example, we must return a location within 1 second.
Within 1 second?
Yes. Right? Cloud-based implementations involves aspects of econometrics. This is really interesting, which is basically when you go and you want to buy an Azure account. You pay for storage. You pay for CPU. Sometimes you have a trade-off between these in the implementation. Should I buy more CPU power or buy more storage? Right? Different implementations of the particle filter emphasize different things. So if there is an objective function to minimize cost, the implementation will be affected by that. platforms, access technology, platforms, sensor stability, antenna patterns. The Android platform has a very different antenna pattern than the iOS platform. So how do I adjust my fingerprint, right? Without actually, I don't want to have the site surveyors to go and collect one time with iOS, one time with Android. Is there something mathematical I can do to my fingerprint rotation, for example, on the RSSI values in order for me to account for the different platforms? Finally, environmental, the network designed for location-based services versus data services, right? If all of a sudden I'm deploying for data services, a completely different animal than deploying for location-based services. Thank you. Thanks.
Okay, thank you very much. And floor is open for questions. First, from our students, any questions? Then, okay, no, our faculty, Dr. Min, maybe you can use this.
Thank you very much for the nice presentation, and I want to ask a few things about the particle filter. You talked about particle filter as based on hidden Markov model.
Yes.
And we know that in hidden Markov model we need to calculate the transition probabilities.
Yes.
So like in machine learning problems, we have offline data available and we can calculate the transition probabilities. But if we are working on an online problem like this kind of problem which you are discussing, the calculation of transition probabilities will not change the location. For example, a system, it is taking time to calculate the transition probabilities, and the target is changing its location. So can we be able to track or locate in a correct time his location?
Okay. For the kind of problem, what you're saying is basically by estimate of the transition probability becomes stale, effectively, right? Invalid, really, or outdated. For the speeds in indoor navigation, this is not the case.
Okay.
So in the system that we're solving, or for the use case that we're addressing, this is not the case. Because as you walk, your RF fingerprint does not change very quickly.
Okay, not changing very quickly. Okay, and the second thing, how good the particle filter compared to genetic algorithm? Because genetic algorithm or similar kind of heuristic algorithms, the particle filter, each particle is producing a solution, and in a way you are trying to fuse the solutions. Yes. Or so.
When I worked on genetic algorithms, and I think that the whole premise is basically from one iteration to another, there is no knowledge. It's an optimization problem where you're changing the population, right?
Yeah.
You change the population and you find a solution. Then you go get another population and you find a solution, and so on, right? But from one iteration to another, the choice of the population is not influenced by in classical genetic algorithm is not influenced by the population in the previous step. Right? That's really the difference between a particle filter and a genetic algorithm. They are a class of genetic algorithms. It's just a refinement, an important refinement.
Yeah. So if you see this in terms like classical adaptive filtering techniques, in the classical adaptive filtering techniques, every filter based on previous knowledge of iteration, they have the previous correction factor.
Yes.
They made changes in the next iteration based on the previous correction factor.
Yes.
So can we think of that particle filters are like many adaptive filters working in parallel, and they are like a CPS decent optimization technique they're employing, or what kind of?
Yes and no. Yes, at a very high level. No, because in steepest descent or Newton-Raphson or all these techniques, there is some form of a guarantee that the next step is going to
converge.
Converge.
Yeah.
So particle filter is not the case.
Not the case. So it's more like heuristic in nature.
It is a heuristic.
Heuristic in nature. Okay. Thank you very much.
Okay. I would like to congratulate you on an excellent presentation. You've done a great job. I'm not in the area. I understood almost everything. Thank you to you. You've done a great job.
Thank you for listening.
Okay.
But question him now.
Yes, indeed. Actually, if the objective I'm looking for is mobile, can we apply the same techniques?
The target is mobile.
لا mobile in the sense in the sense that it is
The target is moving.
the target is moving and you are moving and everything else is moving, you know?
I think you can, but the problem is that actually you probably have to work on a lot of the parameters. So your search space, your fingerprint, has to somehow take that into account.
First, thank you for the presentation. And so my question is, as you say, it's an optimization techniques, and the question is, how likely is the setting parameters affect the convergence of the
Huge
game?
time. Like it's
crucial.
It's crucial.
What is it?
The setting the parameter, the weighting, for example, the weight for the population
I'll give you
size.
the key one the parameters. Let's talk about this. The standard deviation. I have a particle, and I want to move this particle in the fingerprint. I told you I want to choose. So you go back to the fingerprint here. I want to move this particle based on my accelerometer estimate. I want to move and substitute with this particle in the next step. But the accelerometer is just giving you an estimate of the distance, right? So there is a standard deviation there. And you want to account for that. It's critical.
And does it sometimes affect the convergence of the
Very much so.
optimization
If
itself?
you're too slow, for example, with your mobility model, the user will walk outside your space and you will lose it. Yes, very critical.
That's fine. And the second question, now I think the optimal solution for you is to find the exact location. Then how it's likely to end up with the convergence with suboptimal solution? Because this is one of the problems of the genetic algorithm or of the heuristics algorithm.
It's if I understood your question correctly, if I start wrong, how could I converge? Is that what you're saying?
No, even if you start with a good population, but sometimes you could end, even if you have the good exact location,
Absolutely.
but you ended in suboptimal solution that it's far, 5 or 6 meters
Sure.
apart from your exact location.
There are reset techniques. I, for example, discovered that my weights very quickly become very low. And I say, oh, you missed it. Your observation is way out of your search space.
Exactly, yeah.
So you reset. You go back to 0 as if it's time 0, and you do the hypothesis from the beginning. Give me another n equals 500, then let's start again.
I think you did mention that also.
Yes.
The singleton point there.
Yes.
You're coming back to the.
Yeah. You start all over again.
You start all over again, yeah. Okay.
There will be a delay. There will be an outage, but yes, it does happen.
Yeah, okay, thank you.
Okay, I have myself a few questions. I think you already mentioned that regarding the computation burden here.
Yes.
Because, okay, you have a shopping mall and you have, I don't know how many people there. And then maybe you can say a few things about that.
It's today we're solving it using brute force. Just put more power on it. But I think there are a lot more intelligent techniques to do that. Like for example, the simplification of the fingerprint. Right? What does each line add to me? And if you shrink your search space considerably, then all of a sudden your search problem doesn't become, because it's really the most expensive one. Doesn't become as, but we haven't, it's a problem that we plan on looking at and I haven't looked at it.
So basically using like single file decomposition to compose that? And
Yes.
Okay. The other, so okay, reducing the search space, so you're reducing the problem in a sense. Okay. One question, a basic question that I have. I mean, just trying to think loud.
Please.
Okay, suppose that I am in a certain specific mall, let's say Andalus Mall. So it's well-known, everything is there. Maybe I can use my camera, for example, my mobile, and I take a picture. I have an intelligent algorithm. It can really, from the picture, from the whatever, it can tell exactly where I am.
My location.
And then I will use my mobile phone, GPS, all these things, and maybe it could be a less computational problem and an easier solution in a sense to solve at least partially the problem. Okay, I know my space. Okay, with knowing the map of the mall, knowing the whole thing about the mall, maybe the mall has one application where I download it, and then from the picture that I take, It can, of course.
Establish
the-
my location 100%.
Yes.
Okay.
Okay. So this is I have a very good initial condition.
Mm-hmm.
Okay. Now the other devices that I have, like I will call it, I'll use INS because I like INS, Inertial Navigation System. I can use it
Sure.
when I walk, and it can show me in the map.
Absolutely.
Okay. And if I get lost, I take another picture. So this is my measurement update. So
Possible. Possible. But this is a broken user experience. This is exactly what we do. But we don't use the camera. We use the BLE basis.
yeah, but you see that the thing with this thing is that this is a more sure. You don't have all these problems. Things is broken. The devices are changed. Blah blah blah. Whatever. I mean.
Yeah, but it's a broken user experience. You're walking. I walk for 30 seconds, then I have to take a picture.
No, you don't have to do that. You see, nowadays actually the MEMS sensor, these sensors are very precise actually.
They drift.
They drift. Everything drifts. Everything drifts. Yes, but the accuracy is nowadays even with low end sensors is good. And okay, for me actually, because I am in the loop also, so I go there and I want to go to wherever. And I discover that something is wrong. Then I take another picture there.
Absolutely possible.
So it's not really like sort of let it run for.
Loose.
I'm just trying to see something that is a very low end, cheap in a sense, a cheap solution.
You can actually what you're talking about, and our platform allows for this. You can feed the picture into the particle filter.
Okay, you can do that. Yes.
You can it's an opportunity. Yeah, absolutely. You can feed and we talked about that. You can feed the problem is our intuition and observation of the user is you don't want, let's say that if you and I can establish that the best in class IMU sensors today will give you say 90 seconds. Okay.
Best then you have to when you
Best
talk
in
about
class for
review-
smartphone
okay.
industry.
Low end, yes.
Low end. Okay. It's a broken experience for me to stand and take a picture every 2 seconds.
Yeah, but you are assuming that you have to do it frequently. I mean,
2 seconds.
You could fuse actually several things all together.
Absolutely.
And maybe okay.
Yes.
One thing that you know for sure is that for this shopping mall, I know really the map. This is by itself is the map is already stored in the program somewhere in that application, and with these sensors, maybe I'm not saying that you'll get a perfect match, but
there are
I mean,
lots of things that can be done, and you are right. For example, if I take the path, even if it's drifting, I can do a realignment on the map, right? There are things that we're looking at to do that. It is possible. It is possible. But there are many considerations. Psychology of the end users. Today, for example, if you take an 18-year-old and tell me north from south, they don't know how to do it.
you can ask me this question. I will not be able to answer, to be honest.
Right?
If you have to take
Right?
a
So people's usage of the map isn't really all that necessarily. A map is not sufficient. If you go to an Andalus mall and stand in front of a totem, we've done this experiment, observational, just go and observe people. Stand in front of a totem. A totem is where they have the map and tells you are here. And then you are here, okay? And then once you go like this, where am I? Which direction are you in? Right? Where are you? Well, like you get lost, right? So
well, typically, intelligent person, he will see, he will look where the other store in the map, and he can orient himself. Actually, maybe.
It is very. There are solutions out there. There's actually a German company that we've partnered with. It's called NaviVis. They do exactly this. They go in buildings, and they have cards that have cameras, and they capture imagery, and they store them, and then you allow. It is possible. Our solution has the plugins. We don't necessarily. The camera is expensive computationally and expensive from a power consumption point of view to leave it turned on all the time on the smartphone. You don't want to go to the mall for 2 hours and then your phone is completely dead. That's why BLE actually was designed. BLE stands for Bluetooth Low Energy to support these use cases. But absolutely.
Okay. Any more questions, please? Then thank you very much again.
Thank you for having me. Thank you.